So today we discuss application of Biot-Savart law, the very important concept to discuss here, and is very important for board exam and JEE NEET exam also. Okay, so that's the discuss here the application of Biot-Savart law, very important in board exam. Okay, so first we discuss a long straight conductor. First application is a long straight conductor. So we choose a conductor. Okay, and that's supposed be that's called as suppose a origin point. Okay, and here calculate magnetic field at point here, point P, and there is a conductor metallic wire, current passing through that wire in that direction I, and we choose a differential length of that wire, and we consider the length of the wire be, suppose that length be the L, and that the differential length, these are very small amount of length, is called DL or differential length. Okay, so current passing through that wire and create a magnetic field in surrounding. Okay, so here to calculate magnetic field at point P, this point. Okay, so now this length be from origin, that is R, and that point, name that point is A, and that point is B. From A to P, that length is X. Suppose say that X. Okay, I dotted this line, and that important the angle is theta. Okay, from Biot-Savart law we know that magnetic field dB at point P, that is equal to mu 0 upon 4 pi IDL sin theta. Okay, theta, that's the angle between DL or L versus at point P, by, now put where R or X. What is the correct option? R or X? Now you see that from Biot-Savart law, here there is R square. Here the R is the DL2 point P. Okay, distance between these 2 points. So here the DL2, okay, kind direction here, DL2 point P. So that's the X. So that is the X square. Okay. Now simple, calculate magnetic field at point P. So now integrate both sides. So integration of dBp. So we get a magnetic field at point P. Okay, that is equal to mu 0 upon 4 pi is a constant. So outside the integration. So here IDL sin theta by X square. Okay. Now we know that's the current value, the current I, theta, and X. You also know that, but DL here replace the DL. Okay, that's the theta. Now the DL turn into theta. So now simple mathematics. Let some assumption solving the integration. Okay, so here suppose that cot theta, that is equal to cot theta is L. So cot theta is a base by perpendicular. So that is minus L by R, because the current is upward direction. Okay, and here the length consider in that direction. That's a minus sign here. Okay, Now that minus L equal to R cot theta. Now differentiate both sides with respect to theta. Differentiate both sides with respect to theta, and we get minus dl by d theta. So here the R is the constant, and cot, differentiation of cot theta, that is cosec square theta minus, so minus minus cancel, so we get dl equal to R cosec square theta d theta. Okay, now here the cosec square theta. So here that the angle is theta, so cosec means the reciprocal of sine. So means sines, you know that perpendicular by hypotenuse. So cosec is the hypotenuse by perpendicular. That is equal to R hypotenuse here the x by R square times d theta. These are these replaced. So finally get x square by R d theta, that is equal to dl. Now dl put here. Okay. So BP, magnetic field at point P, that is equal to mu 0 upon 4 pi integration I. So dl by replaced by dl. So replace dl by x square by R d theta, here the sine theta by x square. Okay, now x square cancel, that is equal to mu 0 upon 4 pi integration here I by R sine theta d theta, and I by R is a constant, so outside the integration I by R, and integration of sine theta. Now put a limit, suppose theta 1 to theta 2, that's the put a limit here. So mu 0 upon 4 pi I by R. So integration of sine theta, that is equal to minus cos theta. So minus cos theta. So theta 1 to theta 2. So mu 0 I by 4 pi R. Now if I want to cancel that minus, so cos theta upper limit minus lower limit, that's the basic formula. If I ignore that minus sign, so that's why lower limit minus upper limit. So cos theta 1 minus cos theta 2. I step to a 3 step. I jump to a 3 step here. Okay. So get final magnetic field at point P. That's the basic expression. The main expression here. Now I apply some condition or case here. Okay. So applying some case or boundary condition, applying condition here. Condition number 1. If R is much less than L. So here if R, that's actually, don't know why remove that part, and there is a differential length. R is much less than L. So the point P almost overlap with that line. Okay, the conductor line. So now if that portion is true, so the starting point be the 0. So theta 1 be the 0 degree, and the opposite another possibly theta 2, that is pi 180 degree. So suppose these are overlap. If I same direction, so cos 0, sine 0, cos 0, sorry, cos 0, the opposite direction angle be the 180 degree. Okay, if both are in same direction, so angle 0 degree, both are in opposite direction 180 degree difference, so angle between these two lines are 180 degree. So that theta 1 is a 0 degree, theta 2 is a pi 180 degree. Now put the value here. B, we get a mu 0 I by 4 pi R cos 0 degree minus cos 180 degree. Okay, so you get mu 0 I by 4 pi r. Cos 0 here, cos 0 be the 1 and cos 180 be the minus 1. Okay, actually cos curves look like this. So 0 degree, 90 degrees, 180 degree plus 1, that's the minus 1. Okay, so that's the 1 minus of minus 1, so you get 2. So final answer is mu 0 I by 4 pi r times 2, 2 or 2 cancel here 2. So final expression B equal to mu 0 I by 2 pi r. That's the final expression magnetic field if the r is much less than L. Next conditional case here, if the wire is a semi-infinite. So case number 2, where is semi-infinite. So semi-infinite means the theta 1 be that semi means half, pi by 2, and theta 2 is that pi. Now put that value here. So B equal to mu 0 I by, sorry, not 2, here the 4 pi r cos pi by 2 minus cos pi. So cos pi by 2 be the 0. So pi with a minus 1 is plus, so 1. So finally get B magnetic field at point, any point. Okay, choose a point that is mu 0 I by 4 pi r. Okay, that's the final expression. That's a magnetic field. Okay, that the first application calculate magnetic field in long state conductor. Okay, so actually Biot-Savart law help us to calculate magnetic field. Okay, just like that is Gauss's law is help to calculate electric field. Similar concept here, the Biot-Savart law calculate to help find the magnetic field. Okay, now next application is a magnetic field at the center of the circular conductor. Here the application number 2, magnetic field at the center of circular conductor. At the center of circular conductor. Okay, now choose a conductor, a circular conductor. Suppose a circular conductor now look like this. Okay, not a circle look like a circle, but you assume that this is a circle. Okay, and a very good circle. Okay, let's look like a very beautiful circle. Okay, that's the assumption. Now current direction, suppose in that direction. Okay, so calculate magnetic field center of the circular conductor means here. Okay, so calculate magnetic field here, B. So now assume that radius of the circular path is R. Now choose that very small length, differential length is dl. Okay, in that direction dl. Okay, and the current direction I. So this length also be that r because the radius is same. So magnetic field dB, important, dB, that is at center. Suppose that is C, the center point. That is a basic formula, mu 0 upon 4 pi integration I dl sine theta by r square. Here the integration we get, so magnetic field at point C, that is mu 0 upon 4 pi. Okay, now here that I by r square. Okay, and here the sine theta, and the theta is the angle between these two, r and dl, so that we see that's the 90 degree. So I r square sine 90 degree be that 1 sine 0 0. So that's why this term say the 1. See integration of dl. So after solving this, we get mu 0 upon 4 pi I by r square. Integration of dl is the L. Magnetic field at the center C. So here the L with the length. So total length of that circular path. Here the total length of the circular path, that is circumference of the circle. That is equal to circumference is 2 pi r. Yes, 2 pi r, that is the total length. So that is equal to mu 0 upon 4 pi I by r square, that is 2 pi r. So 2, 4 cancel, pi cancel, 1 r cancel. So final expression is magnetic field at the center of the circular conductor. If C is the represent the center, that is mu 0 I by 2 r. That's a final expression. Okay. Then the second application of Biot-Savart law is the magnetic field at the center of circular conductor. Next application of magnetic field is magnetic field on the axis of circular conductor. That's a very important. Now application number 3, magnetic field on the axis of circular conductor. Okay, now here next page, try to draw here. So there is a circular path or maybe the conductor. Okay, now there's the center point here C. Okay, axis of the circular conductor is the C. There is the axis of circular conductor. Now say that is current in that direction. Suppose we say that current in that direction I, and choose a very small length dl here. Okay, that is the ideal direction dl, and radius of conductor be circular conductor with r, and calculate magnetic field here, this point, calculate magnetic field here. So now suppose from C center to this point B, that is called X, that's the name. Okay, and that length represented by U. Okay, so and here the magnetic field in that there is an angle between. Okay, so that's the dB magnetic field here, means that the behind of the dB. Okay, and there's a dB cos theta is the angle is theta, so that is the dB cos theta here, that is the dB sin theta. The dB sin theta is that magnetic field as the axis of circular conductor, dB sin theta, and dB cos theta is the perpendicular of that axis of circular conductor. dB is the perpendicular of the axis, and dB cos theta is the perpendicular to the axis, and dB sin theta is the parallel to the axis, or like the same line on that x-axis, like that. Okay. Someone asks to find that magnetic field on the axis of the circular conductor, so you find dB sin theta. or someone asks to find the magnetic field is the perpendicular of circular conduct axis of the circular conductor, then you find dV cos theta. Okay, how to calculate that? There's a simple mathematics here. There's the magnetic field. Biot-Savart Law, we know that the dV equal to mu 0 upon 4 pi I dl sin theta by here. So see that from here to that point, actually that's the main distance between from dl to that point. Suppose point P, the distance is u, so that is the u square. Okay, so here the angle is theta, there is a 90 degree. So the angle with theta, that is equal to this IDL versus angle u. So that angle be the theta. Okay, the angle, that angle be the theta, and that is 90 degree. This angle with the 90 degree. Okay, so theta with the 90 degree. So that ideal, okay, versus u, the angle is theta, and suppose these angles say the 90 degree. Do not confuse that theta. Okay, that theta, this angle, these two angles are difference angle. Okay, that theta is the 90 degree, pi by 2. So sine 90 be that 1. So I dl by u square. Okay, or here that mu 0 upon 4 pi. So from the axis of the circular conductor, if I calculate the axis of the circular conductor, so choose dB sin theta perpendicular on the axis of circular conductor, that dB cos theta. So here calculate dB sin theta. So we get a dB sin theta. So we get a dB that is equal to mu 0 upon 4 pi I dl by u square. And here is a sin theta terms. These are the component terms. Actually, these are the component terms. Okay, these are the component. Okay, not the actually the not the angle. Angle is that here. There's the these represent called suppose the alpha. Where these two, there's the alpha. Alpha is the 90 degree. Okay, and these are the component theta, that is sin theta, and you see the theta angle is theta. Okay, mathematically these angle and these angle be the same, so that's why these angle theta has sin theta equal to perpendicular by hypotenuse, that is r by u. This sin theta replaced by r by u. Now integrate both sides because there is a dl, so here the db, we get b. So integration outside the integration, mu 0 upon 4 pi is the constant, I r by u cube, integration of dl. So integration of dl be the L. So mu 0 upon 4 pi I r by u cube, that is L. So L means here that circular path. Okay, circular conductor, that means a total length. Total length is circumference of that circular loop, that is 2 pi r. That is 2 pi r. Okay, so now 2 pi is a 4 pi 2. So mu 0 by 2 I r square by u cube. Okay, now here mu 0 by 2 I, okay, r square, and u cube. Here the u cube replaced by from these triangle. Suppose these are the triangle A, B, P triangle. That's the right angle triangle. Apply Pythagoras theorem. The base square plus perpendicular square equal to hypotenuse square. We know that. Okay, from Pythagoras theorem. So that is equal to r square plus x square. Here the u cube, that's the root, means half, and these three here times 3. So finally we get mu 0 by 2 I r square by r square plus x square whole to the power 3 by 2. Now that is equal to magnetic field at point P. Okay. Here is another important term we are missing here also. If the circle is a one loop, one turn here, if there is a n number of turns, if circular loop has n number of turns, now the BP, if there is a n number of turns, so now BP equals by mu 0 capital N I r square by 2 r square plus x square whole to the power 3 by 2 if there is a n turn. Now same case here, if there is a in circular conductor, if there is a n term, if there is n turn, means the loop has n number of turns here, that is B equal to mu 0 capital N I by 2r. Okay. Now here we apply some condition here. Okay. Suppose if x equal to 0. If x equal to 0 means that point P now at the center of the circular conductor. If x equal to 0. So here if x equal to 0. If x equal to 0, then put that BP magnetic field at PP turn into BC center of the circular conductor. So that is mu 0 Ni r square by 2, here the r square x equal to 0. So r square times 3 by 2 to cancel. So here mu 0 Ni r square by 2r cube. The 1r, so BC, that C stands for center of the circular conductor. So that is mu 0 Ni, capital I or small I, by 2r. And you see that the second application, that is mu 0 Ni by 2r. That is mu 0 Ni by 2r. Two expression are is the same here. Okay, the capital I, small I both are the same. Okay, that's very important. That's the basic application of that Biot-Savart law. That's these 3 are in our board syllabus or JEE NEET syllabus we discuss here. If any doubt in application of Biot-Savart law or what is the Biot-Savart law, there is a previous lecture, the definition of Biot-Savart law, okay, and concept of Biot-Savart law, and here we discuss the application of Biot-Savart law. That's very important, and JEE NEET exam also. So today end the class here. If any doubt, always ask in comment section. We will try to give the answer. Next class we discuss the new concept, new topic. Okay. Thank you.